In this video, we're going to do some factoring of polynomials. Specifically, the polynomials I'm going to be factoring will all have two terms. So by now, we should know that that's referred to as a binomial. And what I'm going to be able to pull out or factor is a monomial, a single term factor that is shared between the two terms in this original binomial. What I want you to think about as we factor is that factoring is essentially the inverse of distributing. So I like to think of it informally as undistributing. And when distributing makes use of multiplication, factoring is going to make use of the inverse of multiplication. So we're really going to be dividing common terms out of these binomials as we go along. So without further ado, let's get started. Now, in the first example, and I will show you a couple different ways of approaching these problems. In the first example, what I'd like to do is take each of the terms and break them down as products of their individual pieces. So in the case of 2x squared, I know it's the product of 2. And the x squared I know is nothing more times x times x. Now, when I get to the 8x, I want to take that coefficient of 8 and I want to break it down into its prime factors. So I know that 8 is really 2 to the third. 2 to the third is a product we know is 2 times 2 times 2. And then we can say times x more. So now we've deconstructed the 2x squared into its product and the 8x into its product. And the reason why I'm doing this is I want you to know fundamentally how factoring essentially occurs. With each of these two terms, 2x squared as a product and the 8x as a product, we can begin to match up common factors. So if I see pairs of pieces, as in the case of the 2's, there's a 2 in each of those two products, I can factor them out. And by doing so, I'm reducing those down to 1. So I already can keep track of the fact I've pulled out a 2 as a common factor. Now, looking at the first term, the only, prime factor that there was, in this case the 2, has already been factored out. There's nothing more I can factor out in terms of the common coefficient factors. So now I will move on to the variable components of these two terms. So I will look again. I can see that I have an x and an x. Again, those reduce down to 1, which means that an x gets factored out. As I move along again, I factored out a 2 and an x to go along with the 2 and the x. I see this x here, but it does not have another partner over here. So I've already exhausted all my options in terms of the variable components go. So what that tells me is that I have already found my greatest common factor of 2x squared plus 8x, and that is 2x. What that tells me now is what's going to be remaining is going to be a binomial of the leftover pieces of each of the two terms. So in the case of the first term, I have this x and nothing more, so I can just say x. In the case of the second term, I have this 2 times another 2, so I know that is 4. And I know that those two terms were being added. So this should be my final result when I factor. And what's nice is, since factoring is undistributing, well, I should be able to use distributing as a quick check to make sure this is the correct outcome. So if I distribute quickly 2x times x, I'm back to the 2x squared as the first term of my original binomial. If I do 2x times 4, I'm back to the plus 8x in the second term. And therefore, I know that this is my final outcome in factored form. So that's it. We are done with the factoring. So in the next problem, since we talked about factoring being division, I'm actually going to use a slightly different method. And we'll work our way up to finding the most efficient way of doing this for the last example. So in this next example, I'm going to use the cake method, which you should be familiar with from your days of greatest common factors of numbers. So let's focus just on the coefficients, and then we'll move to the variable pieces of each of these terms. So I know the greatest common factor of 3 and 9 is 3. Now, if I divide 3a to the 5th by 3 by virtue of factoring, that's going to give me a to the 5th. And if I divide 9a squared by 3. That's going to give me 3a squared. You can already see that I've run out of options in terms of being able to factor anything more from the coefficients of these two terms. But that doesn't prevent me from continuing my cake, but now focusing on my variable terms. Now, I want you to understand something. When I have an a to the fifth and I have an a squared, the highest power that I can factor out is going to be driven by the lowest power of a in the individual terms. So I can't pull out anything more than an a squared right now. Because if I tried to do so, I wouldn't have anything more here to factor out beyond the a squared. So let's take a look at that. Now this is where your quotient rules come in. Okay, so that's another important thing. Think about the exponent rules we learned. This, by factoring, we're simply saying a to the fifth divided by a squared. And we know in that case, all that we do is subtract the exponents. So I get a to the third. So a to the fifth, factoring a squared out, dividing by a squared gives me a to the third, minus 3a squared divided by a squared. Well, again, I can focus on those variable terms. 2 minus 2, because it's the quotient rule, means I wind up with essentially a to the 0, which is the equivalent to 1. So now I have 3 as all that is remaining. Now, if we remember about greatest common factor, that's made up of the product of these two terms. So that's going to be the outside. That's going to give me 3a squared. And remaining in a binomial should be what's at the very bottom of our cake, a to the third minus 3. And one more time, if I quickly distribute, I should confirm that I wind up back where I started. So 3a squared times a to the third, product rule, add the exponents, that gives me 3a to the fifth. Minus 3a squared minus 3, I can multiply my blue coefficient terms. 3 times 3 is 9, with the a squared coming along for the ride. So that is that. Okay. So now that we've seen two slightly more inefficient approaches, what we're going to do is on the last one is take the most efficient approach. We're going to focus on the coefficient terms first. So let's see. The greatest common factor of 15 and 12, I know is 3. And I'm going to start to build my binomial as I go, so I can keep track. 15 times 3, I know is 5. I'm going to leave some space. I'm going to put my plus sign in, and my space here is for the variable that's going to have to be accounted for here. 12 divided by 3, we know, is 4, and I know I'm going to have a variable term here. Okay, so let's see. 3 times, whoops, let's try that again. 3 times 5. 3 times 5, I know, is my 15. 3 times 4 is my 12. So I'm looking good so far. Again, when we focus on the variable, the greatest power I can pull out for the variable term is based on the lowest power in the original binomial. So I can pull out a y to the fifth. I can factor out a y to the fifth. Let's see. Y to the eighth divided by y to the fifth. Subtract the exponents. That gives me y to the third. Y to the fifth divided by y to the fifth. That's like y to the 0 or 1. There's nothing more. I'm done. So if we factored correctly, we can quickly check by distributing. 3y to the fifth times 5y to the third. 3 times 5 is 15. Y to the 5 plus 3. Y to the eighth. 3y to the fifth times 4. 3 times 4 is 12. Y to the fifth. So one more time, I am done. So all that you're going to do, and what I'd like you to do is really to try to use this strategy moving forward, but you've got some other fallbacks so that you know kind of the math behind it, a little more substance. But I want you to factor these last 3 binomials, and I posted the answers up for you so you can take a look at the end results. We'll check in more and do more practice when we see you next.